Alright, I'm going to get into this review and do numbers 31 through 60, but first I'm going to correct some mistakes from the first 30. So in number 9 here, in the first 30, I got caught up with this negative infinity, and of course the highest power is on the bottom, so it's just going to go to 0. Doesn't matter about the negative signs, because if you're going to 0, you're going to 0. 0 equals negative 0. True fact. Let's see. There are a couple other mistakes too. Maybe not on that page. Or this on this page, I think the only thing that I did that I regret is that in the inverse problems, I labeled these as F and F prime instead of F inverse. I meant to write F inverse there, so I fixed that in my little answer key here. And let's see, in numbers 23 and 24, I guess because of this here, I also did h prime of 2. So my derivative taking was all correct, but I plugged the wrong thing in. So I fixed those and got 4 for number 23 and 19 over 25 for number 24. Those are the correct answers. These are correct. The other ones are correct for h prime of 2, but that's not what we were asked to do. And then 28, I had the wrong y coordinate here. So we know that the x coordinate is -4, which I talked you through in the last video, and then when you plug -4 in here to find the y coordinate, you get -4. So, no, sorry, you get +4, because -16 plus 20. So that's 4 there. I don't even remember how I got the 3, and I'm not going to go back and look at the video to experience that mistake, so you can figure that out if you want, but this is the right answer. Alright, sorry for that. Here we go into the next 30. Draw a tangent line to the indicated point, like this, and fill in the blank for each picture. And when we say, sorry, if this wasn't clear, fill in the blank with greater than or less than sign. So here, our linear approximation is going to be greater than, because it's increasing concave down. Here, it's my tangent line. It's my linear approximation here is less than the actual value. The actual value would be on the function. And that's increasing concave up, and then decreasing concave down. My linear approximation is greater than, and here it is less than. So you can see the thing that matters is not the increasing or decreasing. It's not the first derivative of this, it's the second. So if your function's concave down, your linear approximation is going to be bigger, and likewise if it's concave up, it's going to be smaller. All right. Shuffle my papers around here for a sec. All right. The mean value theorem, in a nutshell, says that your average slope is going to be attained, realized somewhere in between 2 points if you have a curve that is continuous and differentiable. And when we have to, in cases where we have to invoke the mean value theorem, these are the magic words. That is the incantation that you have to say before you can wave your wand and make it happen. So if it is continuous and differentiable, that means we can use the MVT. For all values 2 to 5, f of 2 is equal to -3, f of 3 is 4, f of 5 is -3. Then on the interval 2 to 5, what can be said about the slope? Well, here the slope is equal to between 2 and 3. The slope would be 4 minus -3 over 3 minus 2. So there's a slope of 7 there. If I go from 3 to 5, then I have negative 3 minus 4, 5 minus 3, that's negative 7 halves. And if I go from 2 to 5, then they have the same y value. So what can I say about the slope? I can say that it's got to equal, by that mean value theorem, it must equal all three of those. Right? On each one of those little intervals. How many extrema? Well, if we're going from f of 2 and then we're going up to 4 and then down to negative 3, then there's only guarantee of 1. I know that I'm going up. Hold on. Let me think for a second. Yeah, I know I'm going from negative 3 up to 4 and then back to negative 3 again. So could it have more maximums or minimums? It could, but it doesn't have to. So only one guaranteed there. Find the average rate of change for f of x is equal to this on negative 2, 0. So the average rate of change is the slope when I plug in negative 2 in here. That gives me negative 4 plus 8 plus 3. Negative 4 plus 8 plus 3. I'm feeling like that's equal to 7. Let's see, let me just check that, make sure. So negative 1, yes, feel good about that. Minus, when I plug 0 into this, maybe I should write here, sorry, I'm going to add one other. Okay, this is what I'm doing. So that's 7, f of 0 is 3, negative 2 minus 0, that's 4 over negative 2, or negative 2. That's the average rate of change on that interval. For what value of c, in between 0 and 3, is the instantaneous rate of change for this equal to the average rate of change? That's the mean value theorem again. So here, I want to find f of 3 minus f of 0 over 3 minus 0 and set that equal to f prime. So f of 3, 9 minus it's 3, minus 0 over 3 minus 0 is equal to, the derivative here is 2x minus 2. So it looks like c is going to be equal to 3 halves. Find the average velocity of a particle on this interval if the particle's position is given by this, where t is measured in seconds and s is measured in feet. So average velocity is equal to change in position over change in time. In other words, it's just like a secant line slope, old school slope. So s of 3, plugging 3 in here, negative 9 plus 15, that's 6, minus plugging 1 in here, and get 4 over 3 minus 1, that's 2, and that would be in feet per second. Just going to double check that real quick. Try to avoid as many mistakes as I made yesterday. Yeah, I think that looks good. Okay, at what time c does the particle reach its average velocity? So that's saying, okay, well, mean value theorem, the derivative of this must actually equal that somewhere in that time interval. So the derivative of this is negative 2t plus 5. So I'm going to set that equal to 2 and subtract that, so t is equal to, let's see, I don't like the answer that I'm getting here. Oh, that's because 6 minus 4, this is equal to 1, not 2. 2 over 2 equals 1. So, fix that. And then t is equal to 2. That's better. All right. This is a mean value theorem action. And here, the extreme value theorem is the when you have a closed interval, if you have a continuous function. So for mean value theorem, I'm going to write in these little boxes or next to them what must be true before you can invoke those. For this, you have to have continuous and differentiable. For the extreme value theorem, you only have to be continuous only. If it's also differentiable, that's great, but it doesn't have to be. So we test the endpoints, and then C star CS. This is anywhere where f prime is 0 or undefined. All right, those are the points we test. Sometimes this is called the candidates test. So the candidates are the endpoints, got to check those, and anywhere in between where the derivative is 0 or undefined. So here, I'm going to take the derivative, and set that equal to 0, and get x is equal to -2. And then I'm going to make a little table, and I'm going to test my 3 candidates, -3, -2, and 0. And when I say test them, I mean find the function values for them. So when I plug -3 in here, I get 9, -18, plus 24 is 6, plus 2, I think that's 8. And then when I plug -2 in, I get 4 times -2 is -8, plus 16 is 8, plus 2 is 10. And when I plug 0 in, I get 2. So this is my absolute minimum. And, oops, not that. 10 is bigger than 8. Don't you know? That's my absolute maximum. Alright, same deal here. Just going to do it again. Practice makes better. 2x minus 1. I'm going to set that equal to 0. Okay, so my candidates are the endpoints and 1/2. All right, let's plug those in. When I plug 0 in, I get -6. When I plug 1/2 in, I get 1/4 minus 1/2, which is minus 1/4 minus 6. That's minus 6 1/4. And then when I plug 4 in, I get 16 minus 4 is 12, minus 6 is 6. Just double checking that, 16, 12, yep. So it looks like this right here is my absolute minimum, and this right here is my absolute max. Let me just make sure that that was on screen. Put that there for just a sec. All right. Slope and concavity. Critical points. Here's some good definitions to have all in one place. Critical points are where the derivative is 0 or undefined. Increasing intervals, it's going to be where your derivative is greater than 0, decreasing where your derivative is less than 0. So therefore, minimums must happen where f prime changes from negative to positive, and maximums likewise derivative is going to go from positive to negative. Points of inflection are where the second derivative is 0 or undefined and has a sign change. So you got to watch out for that. You need the sign change for a point of inflection. For a critical point, don't need the sign change. Intervals that are concave up, that's when the second derivative is 0, and by definition, again, the concave down is where the second derivative is negative. All right. Here we want to find all critical points, increasing, decreasing intervals, and all mins and maxes. Okay, so I'm going to find the derivative, 3x squared minus 2x minus 5. And I'm going to try to factor that. Cross my fingers. Uh-oh. Does this not factor? That's a bummer. No. Wait. Yeah, it does factor. Sorry. 5 here and a 1 here. Yeah, because then with the minus sign here, that's minus 5x plus 3x. That gives me the minus 2x. Whew, that was close. So the critical points are at x equals -1 and 5/3. And the increasing, decreasing intervals and mins and maxes, you can set up a sign chart and do that. Maybe I'll make the little sign chart. This is a sign chart for f prime. And I know that it's going to change signs at those places. But I know what this is going to do. I mean, it's a cubic function with a positive leading term. So it's going to look like this. So I know that it's increasing, and then decreasing, and then increasing again. So I know the first thing that we come across here, there's a maximum at x equals -1, and there's a minimum at x equals 5/3. And our justification, f prime, goes from positive to negative, and this is a minimum because f prime goes negative to positive. All right. Find the x location for all local extrema for this. Same game. It's x squared minus x minus 2. Let's set that equal to 0. And I'm going to factor it. Oops. It's x minus 2, x plus 1. So at x equals -1 and x equals 2. That's where my local extrema are. If you want to know, this is also a cubic function with a positive leading coefficient, so it's the same. This has to be a max, and this has to be a minimum. Number 43, find all points of inflection and indicate the concavity over each interval for this function. So concavity and points of inflection is the second derivative. Let's get there. 5, that's 1/4 x to the 4th plus 1/2 x squared plus 2. Second derivative, x cubed plus x, and set that equal to 0. Going to give me x squared. So my candidates are at x equals 0 and x equals -1. If you made a sign chart here for the second derivative, put -1 and 0 on it, you're going to find that -1 on this side of -1 is going to be negative, and then positive again, that you don't get a sign change at 0. So points of inflection are at x equals -1 only. Why not 0? Because a point of inflection has to have a sign change, and we don't get a sign change there. And then the intervals of concavity were concave down when -infinity to -1, and then concave up everywhere else. All right. Second derivative test for finding maximums and minimums. If you've got a critical point, that means where f prime is equal to 0 or undefined. Then if the second derivative is greater than 0, so this is like a place where the derivative is flat, right? It's flattened out. If it's flat, if that's true, and the function's concave up, you must have a minimum. And likewise, if it's concave down, you've got to have a maximum. So that means that here, the derivative is 0, and it's concave down. So the derivative is 0, and the function's concave down. So f of 2 is a maximum. All right. Curve sketching. So this is like taking a function or its derivative and then sketching the other thing. So here I have f, and I want to sketch the derivative. I'm going to try to do it right underneath here. I'm going to jam it in here. So if I'm trying to graph a derivative, I'm trying to graph the slopes of this. Here's a place where the slope is 0. It's going to make a 0 there. Here's a place where the slope is 0. And then on my way toward this, I have positive slopes, so I'm going to be positive territory. And then in between this and this, I'm decreasing, so I have negative slopes. And then after that, I have positive slopes. So any kind of like parabola-looking thing with zeros there and there. Here's a second derivative. And we want to get all the way back. Oh, sorry, we want to graph the second derivative, and I have f here. I'm going to go ahead and graph the first. Oh, I have that. It's the same thing, isn't it? The same function. Okay, so I'm sketching a graph of the second derivative of this, which is the same as sketching a graph of the derivative of this. So, trying to squeeze it in here again. First thing is I'm going to look for places where the slope of this is 0. Somewhere like there maybe. And then the slopes of this are negative and then positive. I'm going to make that a straight line because this looks like I'm also drawing on my knowledge of derivatives. If this was like an x cubed kind of thing, then this would be an x squared kind of thing, and this would be an x kind of thing. If you did something, a little variation on that, and it's just like going up the whole time, that's good. That's fine. So here's a graph of f prime. We want to get back to f. I think most of my students would agree that this is a little harder. So this is a graph of the slopes. So I have something that is it's increasing. This is a graph of the slopes. It's going up this whole time. It's going up steeper, flattens out for a sec, and then gets to be steeper again. And then here it has like a constant slope. That means it's going to be like a straight line. And then it's still increasing, but less rapidly, and then finally decreasing at the end there. So it's got steep, maybe something like that, right? Steeper negative slopes, and then it's got a slope of 0 right here, but immediately it starts to get back into positive slopes again. And then when it gets to here, it goes straight for a little bit. And then this starts going down, but it doesn't mean this starts going down. It just means that this starts getting less steep. Not until here. This is a place where the derivative is going from positive to negative. That's a maximum. So somewhere up here, I get to that maximum, and then on the way down from there. Now I want to sketch the second derivative. This is a derivative, so I'm sketching the slope of this. Here's a place where the slope is just 0 for a while. And here's a sharp corner and another sharp corner. It's going to show up as open circles on this. And I'm making the graph of the slope of this. Here's another place where the slope is 0. Okay, so here the slopes go from negative to positive, and then all of a sudden there's a jump from that positive slope down to slope of 0. And then there's a jump into having negative slopes, but that's just a straight line, so it's the same slope. So something like that. A little tricky. How about slope and concavity from this graph? At what point is the derivative less than 0? So that's decreasing. That could be B or C. And concave up. Now it looks like that's still concave down, so I thought it was going to be C, where it's decreasing and concave up. Part of the smiley face. At what point is the function less than 0? That could be C or D, and f prime is greater than 0. That's increasing. So that's going to be at D. If g of x is equal to f prime of x, then at what point is g of x equal to 0 and g prime of x less than 0? Okay, so g of x is equal to f prime of x. So I'm just going to rewrite this. What point is g of x, in other words, f prime of x less than 0, and g prime, in other words, f double prime, less than 0? So we want both. We want decreasing, concave down, decreasing, concave down, decreasing, and those are the decreasing ones, and concave down, so that's B. Answer the following based on the given graph of f prime. What are the critical numbers of f? The critical numbers for f are those. Looks like about -2 and 1. Oh, just kidding. This is a graph of the derivative. Sorry, I'm looking at those. So I'm one level off. That's a common mistake to make. Don't do that. Critical numbers for f are f prime is equal to 0 or undefined. So no places where it's undefined, but it's equal to 0 at -3, 0, and 2. Where does f have relative maximums? So maximum is going to happen where the f prime goes from positive to negative. So f prime is going from positive to negative here and here. So that's at -3 and 2. What are the locations for the points of inflection of f? So points of inflection, that's where its second derivative is equal to 0 or undefined. And that's the same as saying the derivative of the derivative is equal to 0. And this is the derivative. So I'm looking for places where the slope of this is 0. That happens here and here. So that's my, at approximately -2, and 1. That's what I started to do there on number 52, 51. All right, about a half page left for this video. What are the locations for the points of inflection of f? This is a graph of f double prime now. So the points of inflection are where f double prime changes sign. And that happens here and there only, because this is an actual graph of f double prime that I'm looking at. What are the critical numbers for f? The critical numbers are where f prime is equal to 0. And without knowing some value, if you think about like fundamental theorem, if I want to get back to f prime is equal to integral from somewhere to x. But unless I know about the somewhere on that derivative function, then fundamental theorem is going to give me something that, like, I don't know what the critical values are going to be, because that function could be lifted up and down. So I can't actually say. Not enough information. Number 56. Use the given graph of g prime to answer the following about this function on the interval from -3 to 3. Find the values of for which g has local extrema. So this is a graph of g prime. So g has local extrema when g prime changes sign. Now, looking for critical points here. Critical points would be a good place to check, but if we just want extremes, extremes are going to happen when you go from increasing to decreasing, or vice versa. So where g prime changes sign, that happens here. Not here. This is going to be, the g function would be increasing but getting flatter, attaining a slope of 0 just for an instant, and then increasing again. Sorry about those announcements there. They will pass quickly. Intervals on which g is increasing. G is increasing when g prime is positive. G increasing means g prime is positive. So that's from -2 to 3. Find the values of g where g has a point of inflection. G has a point of inflection where g double prime changes sign, which is the same as where g prime changes sign, or in other words, where this graph, the slope of this graph, changes from positive to negative. So that's the same as the maximums and minimums of this. It's a good thing to know, if you've got the memory space available for that fact, that if you're looking at the graph of a derivative, the points of inflection are the maximums and minimums of that. And they can be pointy. That still works. So that's at x equals -1 and 1. State the location and classify the extrema on g double prime. So what are the peaks, the extrema on g double prime? Let's see. What would g double prime look like? I'm going to make a quick sketch to help me answer this. G double prime is the slope of this. So the slopes of this, 0, 0, and these are going to be positive slopes to here, but getting closer to 0, and then negative slopes, but not getting too negative, and then positive there. So the extremes of G double prime, that is right there, at x equals 0, G double prime has a minimum. And then they want me to sketch a graph of G. Okay, getting back to G, I'll put that up here. Now, I don't know, I don't have any information about like a point that the G function has to go through. So I'm going to sketch it, but if you sketch something that's very similar and like moved up or down, I don't have any information about the plus C. So, so there you go. So this looks like a cubic, and so I'm thinking this is like 4th degree, right? So these are the slopes. Here's a place where the slope is 0, and going from negative to positive. The slopes are going from negative to positive. So that would be a minimum. And here is a place where the slopes are going from positive to positive. So that's like one of those spots where it looked like it was going to be a maximum, but then it changed its mind and decided to go back up again. So we have something that looks like it's got a minimum here. It has an inflection point here. That's where it goes from bending up to bending down. And then it bends through here, thinks maybe it's going to have a maximum, but then it changes its mind and comes back up like this. So something like that. And that's it for this batch of problems.